Welcome to Data Science with EJD. From the last video, we started talking about validation and tuning in supervised learning. Don't forget, you have access to my code sheets and data sets by just looking at the description box in whether on YouTube or on Facebook. It will take you straight to a Google Drive where you can download all these code sheets. And I always advise download first and then follow along. Do as I do so you can actually get it because you code by coding. When I started, I could watch several videos, and then by the time it's time to implement, I was too tired to even try. Okay, so you want to do that, and be sure to subscribe to the channel if you have not done that already, and check out the membership options to get some special privileges. All right, so our focus here is on grid search for hyperparameter tuning, since our focus generally in this set of videos will be is on validation and tuning in supervised learning. So we've been doing, I mean, in the last video, I gave a kind of snippet about hyperparameter tuning, but here we are looking at it like in depth. So grid search for hyperparameter tuning. So first of all, what is hyperparameter tuning, right? Hyperparameters are configuration settings that are external to the model and they are set before training. So things like maximum depth, like in the snippet I gave, I talked about maximum depth of trees, number of trees, n estimators in a forest, right? Then proper tuning of hyperparameters is critical to optimize model performance, right? So after training your model and you get some kind of result that you're not satisfied with, you may consider hyperparameter tuning. So if you already have an excellent result that you like, you don't have to worry, right? So it's this is like trying to optimize just like how you try to optimize a code that is already doing well. You just want to maybe write it in fewer lines or something like that. So this is what hyperparameter tuning is like. You want to get your model to perform as excellently as possible. So unlike model parameters learned during training, hyperparameters govern the training process itself. So why tune hyperparameters, right? You want to improve model accuracy and generalization. Like I said, you want to also prevent overfitting where you have too complex model or underfitting where you have too simple model. Then you want to achieve optimal bias variance trade-off. So there's bias, there's variance. So you want to have a good trade-off of both. So grid search now, talking about grid search, right? So grid search CV, grid search cross validation is one very important tool we use here. So because we're talking about grid search for hyperparameter tuning, so the concept of grid search is such that it is an exhaustive search technique over a specified parameter grid. So you have things set in place, and then you do a comprehensive search over the grid you have set out. So talking about the number of trees, the maximum depth, and things like that. So it actually trains and evaluates the model for all possible combinations of hyperparameter values. So it's more like it checks all the possible options and settles for the best. And it identifies the combination that yields the best performance metric, like I just said. So how grid search works? The first thing is you specify a set or grid of hyperparameters and values to test. Then for each combination, you trade the model, validate using cross-validation or a validation set. Then you can select the hyperparameters corresponding to the highest validation score. So like in the snippet I gave in the last video, right? So we had I think 100, 200, 500, grids like that. And then with their corresponding depth and number of trees and all of that. And then at the end of the day, we discovered that the best was the one with 50, hyper 50 trees or so. And then the depth was none, like unlimited depth, so to speak. Now, 24.3, talk about tools. So GridSearchCV in scikit-learn, so we can get GridSearchCV. GridSearchCV automates grid search with built-in cross-validation. So it splits data into folds, e.g. five-fold cross-validation. So I mean, the most common folds we have, like we said already, are 5 and or 10, but we've been using 5 all for the most part since we started mentioning k-fold cross-validation. So it splits data into folds, e.g. five-fold cross-validation, trains and validates on folds for each parameter set. It returns the best hyperparameters and trained model. So supports parallel processing for speed. So you have n jobs, so you have parallel every things happening at the same time. And it can allow specifying scoring metrics like if it is accuracy you want or ROC or AUC and all that, you can actually specify. But we've been using accuracy for the most part, especially when we're doing classification jobs. So you can also target model and hyperparameters. So example model, if you have a random forest classifier, for instance, so a random forest classifier is an ensemble of decision trees. So just like you know what a forest is, right? So one tree doesn't make a forest for sure. So you have an aggregation of different trees, evened out over time. I mean, averaged out to get your random forest. So the key parameters to tune are usually the maximum depth, that's the maximum depth of each tree, which controls the complexity of the tree. Then the N estimators, that is the number of trees in the forest, which affects model robustness and training time, right? So once you can tune this properly, you can be sure you get a very nice model to work with. So step-by-step guide to grid search tuning. Step one, you prepare the data, load the data set. I mean, we've been loading data sets since we started talking about data analysis with Python and split into training and testing sets to evaluate final performance. And if you're using K-fold or all that, then you would have done that, right? Then define the model. You initialize the random forest classifier with a fixed random set for reproducibility or any other model you're using for that matter. Then in step three, you define the parameter grid, right? So you choose ranges of values for each hyperparameter. For maximum depth, you can choose 3, 5, 10, and or none. For N estimators, you can choose 50, 100, 200. You know, it's so the maximum depth, it's more like I can see maximum depth as maybe the number of branches on a tree, while the number of estimator is the number of trees that make the forest. So you can consider it that way. So create uh, grid search cross-validation object. So you pass the model, parameter grid, and number of CV folds, scoring metric, verbosity, and parallel jobs. That's the next thing you do in step 4. In step 5, you fit the grid to search you feed the grid search to training data. So you now after you've fit the model, right? Okay, you train and validate for every combination in the grid. And number six, finally, you evaluate and extract results. So you retrieve best hyperparameters and best cross-validation score. Then use best estimator to predict on test data and calculate final test performance metric. A very good example is what we have here. We have a complete example code. So we are using Iris dataset again because it is very simple to work with, especially for educational purposes. Let me bring line numbers for easy referencing. So, yeah, so from lines 1 to 4, that is us mounting the necessary libraries for the task ahead. So you have sklearn.datasets, you import load iris because you're using iris dataset. Then we need grid search CV and train test split from scikit-learn model selection. Then we need random forest classifier from the sklearn ensemble. We need accuracy score from sklearn metrics. Then step one, you load data and split. So data is load iris and xy data.data. That gives or that will give us the features, while data.target will give us the target or the output. So, and then in line 9, now we are splitting the data set into 80% for train and 20% for test. But by just indicating test size is 0.2, that works well enough. Then in step 2, initialize model. So we have random forest classifier. So random state is for the two to ensure that we always get the same result. In step 3, we define the hyperparameter grid. So maximum depth, we have maximum depth of 3, 5, 10, and none. That none means unlimited depth, as I said the other time. Number of estimators, 500 and 200. Now, for you to know the seriousness of what is happening here. So in the tuning process, right? It takes it's to take a maximum depth of 3 and try it with 500 estimator, 50 estimators, 100 estimators, 200 estimators. You know, that's like four. If it's more like a four times, that's like 12 possibilities, right? That's 4 times 3 possibilities. So 3 on 50, 100, and 200, 5 on 50, 100, and 200. So it's take a maximum depth of 5 and try it across 50, 100, and 200 estimators each. Then it's take 10, try it across, to take maximum depth and try it across like that. Now, that is unlimited depth and try it across. And then at the end of the day, it outputs a result that gives the best cross validation score. So you have grid search now. You have grid search CV estimator So you use the random forest classifier. Parameter grid is the parameter grid you mentioned here already. CV is equal to 5, right? So that's a five-fold cross-validation thing. Scoring is you want to see, you want to decide which is best based on accuracy. All right. So you're optimizing for accuracy. Then N jobs is minus, and that's use all CPU cores, and verbose that displays the progress. So verbose is what makes you see how the tuning process is going line by line. Okay, then you can in step 5 you fit the grid search. So you have grid search dot fit the grid search you have set here dot fit x train y train. That's you training the model right there. And in step 6 you extract and display best parameter scores. So you have best hyperparameters, grid search dot best params. That's how you get that. Best cross validation accuracy, you have grid search dot best underscore score underscore. Then in lines 36 to 38, you evaluate on test data. So best random forest, you have grid search, best estimator, y predicted is best random forest dot predict x test, and then you print the test accuracy. Now I could actually split these things up, but it's okay if I also I'll leave it this way. So I just press enter, I mean control enter, run the code. So you see, the verbose is what makes it tell us this that it's fitting five folds for each of 12 candidates. You know, I told you 12 possibilities, and that is totaling 60 fits because you have five folds. So the best hyperparameters after all the processes, maximum depth of 3 and number of estimators 50. That's what works best. And the best cost validation score is 0.95. The test accuracy is perfect, 1.0, 100%. Of course, that can be due to the fact that the iris data set is pretty straightforward. You have 50 flowers categorized into three species with 50 of each species, basically. So it's really straightforward. That's why it's a very good one for trying out some of these things. Okay, so let's look at some detailed explanation. When we talk about maximum depth limits the depth of each decision tree to control over fitting. So typical values to test will be 3, 5, 10 or maximum. Then N estimate, so that number of trees, that is more trees usually improve accuracy, but increase computation, right? Um, all right, so that's typical values to test for would be 50, 100, and 200. So CV equals 5 actually tells us that we have split training data into 5 parts, training on 4 and validating on 1, rotating through all folds. So it's such a rigorous process that by the time the result is out, yeah, you can be sure of the you have it's more reliable, right? So it's more like the first time you're trying, you train on 4, you hold one out to evaluate. Then next time you pick another one as your test data, and your training data is shifted to the other 4, including the one that you used initially. So by the time it's all done, you get a fairly better result. So n jobs equals -1 means it runs all parameter combinations in parallel to speed up grid search, so that so it's more like some kind of parallel computing happening to make things very fast. So verbose equals 1 shows progress and status messages during fitting. So that fitting 5 folds for each of 12 candidates, totaling 60 fits, is actually the job of verbose. If you don't do verbose, you don't see that. And of course, if you don't need that, like especially what I remember, was it when we're talking about deep that visit to deep learning, neural network kind of thing. So you see all those epochs, like it shows you step by step. Like you have 50 epochs, it keeps showing you what is happening, the error, the accuracy, and things like that. So, what are some best practices and considerations when we are doing hyperparameter tuning with grid search? So best practice and considerations. First, you start small. Use a coarse grid with fewer values to identify promising regions. Then you can refine the grid. So after initial tuning, you narrow ranges or add intermediate values. Then balance compute time. So grid search can be expensive. So you can consider randomized search CV for large hyperparameter spaces. So here we are using grid search cross validation, but another option will be cross randomized search cross validation for large hyperparameter spaces. Then you can use stratified CV. That's difficult for the default for classification to maintain class proportions across folds. Then if class proportion maintenance is your deal, then you don't just want to use K fold, you want to use stratified k-fold cross-validation. Then set the random state for reproducibility. So be sure that you get the same result each time. Then you can also scale up reprocess data if required by your model. Most machine learning models prefer, instead of having objects, you can, do some encoding so that although it is still object, but then the encoded thing makes it easier for the model. In summary, grid search is a powerful systematic method for hyperparameter tuning. So grid search cross-validation integrates cross-validation to robustly evaluate parameter combinations. Tuning maximum depth and N estimators in random forests controls model complexity and robustness, right? So the best parameters discovered via grid search often yield significantly better predictive performance on unseen data. So this brings us to the end of the video. Let me know how helpful this is for you, and be sure to um like and share so that more people can have access to the videos, to the content I have on this channel. And of course, don't forget to subscribe if you haven't done that already, right? Then also hit the notification bell so you can always get alerted each time a new video is released. Then I have membership on my channel now, so just check out the options and see which part you like to belong. Till I come your way again next time, keep doing data right. Bye.